This video is an introduction to the use of vectors. Let's consider situation 1, the brave duckling. So a mother duck shelters by the bank of a pond with her young family, but one brave duckling ventures out for a swim. The duckling swims 5 metres on a bearing of 50 degrees and then 7 metres on a bearing of 170. We want to find out what distance the duckling has swam altogether, how far the duckling is from its mother at the end of this little excursion, and the bearing of the duckling from the mother. Now hopefully you've got these floods of ideas coming through from previous years to do with trigonometry and using the cosine or the sine rule. So first of all, we need to draw a diagram. Now if we consider the mother duck and the duckling swimming on a bearing of 50 degrees for 5 metres, and then it turns and swims on a bearing of 170 degrees for 7 metres. So very quickly we can get a bit of a picture of the duckling's movements. But each movement that we have here is represented by what we call a vector. A vector is just a quantity that measures a magnitude and a direction. So magnitude meaning size. So here we've got the displacement of a duckling from its mother. So when we draw a vector, we can draw a straight line either with an arrow at the end or an arrow in the middle. And that just helps us show what direction in our diagram that the duckling is swimming on. So once the duckling has left its mum and swum its 2 stages, it is at rest, which means we can see the duckling has swum a total distance of 12 metres. But its displacement is not 12, because its displacement is how far it is from its initial position. So to find this, we need to actually look at what we call the resultant vector. So I'm going to put a little R here with a little wave underneath, and I'm going to call it R for resultant vector. Now, when we're dealing with a vector, we either have the letter with a little tilde underneath it, or we can write it in bold, but it's hard to know what's in bold and what's not in this video. We could call our first vector A and our second vector B. We can call the magnitude of A, and the magnitude is the size, and we put that in the 2 straight lines, and we can say that was 5 metres. And we can do the magnitude of vector B, his second stage, and that would be 7 metres. And what we notice is that we've got these lines representing our vectors are what we call positioned as nose to tail, which means the start of the vector to the finish of the vector. Then from the finish of the first vector, the nose and the tail, again, start of the next vector. So we've got the nose here of our first vector, and the tail of our second vector starts until we get to the nose of our second vector. So that just shows that we're adding on from one vector to another. And if we follow the directions of the arrows, we can see the final direction that's going to happen for our resultant vector, our displacement that we want to find. So in this case, I can see that I have got to do some calculations with some angles and parallel lines in our north points. That can help me here, and that will help me recognise that the angle in here is 60 degrees. So from there, what I can actually do, because that's opposite the side I want to find, I can use the cosine rule. So I've used my trig to solve here, using the cosine rule, 5 squared plus 7 squared at the sides. Take 2 times 5 times 7 times the cos of 60, the angle in between the 2 sides, and opposite the resultant we want. And I've square rooted that to get the square root of 39 metres. I'm going to leave it an exact value, that's fine. So now what I'd like to answer is, what is the bearing of the duckling from the mother? So I actually need to find this angle theta and add it on to the 50 to get the bearing from the north point. So here I can then use the cos rule again. Phi squared plus r squared take 7 squared, which is opposite the theta, over 2 times 5 times r. And then I can work out that this is going to be 76 degrees. So this means, if we have a look, that the duckling is 39 metres from its mother on a bearing of 126 degrees. So as a bit of a summary about vectors, we can use a line segment to show a vector. Here's an example of a line segment from point A to point B, and it's got the arrow to show its direction, and we've called it vector R. Its magnitude can be either written by the letter it's given or by the points that bound it. So a vector has magnitude and direction, so we use this for displacement, velocity, force, acceleration, whereas a scalar is just has magnitude, a quantity with magnitude, just size, so things like distance or speed or energy. In our second example, we're going to have a look at some forces. We'll have a look at 4 different scenarios of tugboats towing a floating platform. What we want to do is determine the total force and the direction of this force on that square platform from the tugboats. So in our first example, you can see that we've got our platform and we've got one tugboat heading directly north and with a force of 5,000 newtons. So we can clearly see that the force here on the platform will be 5,000 N in a direction of 0 degrees. That will be the resulting vector that we can draw in. So we could actually show that as R. In our second example, we've got 2 tugboats pulling the platform. They're both exerting a force of 3,000 newtons. So that's really going to force that forwards. And our resulting vector obviously is going to be directly north again because the tugboats are heading directly north. So our resultant vector R will have a magnitude of 6,000 and in a direction of 0 degrees. In our third example, we have 2 tugboats acting on this platform, but they're not pulling them directly north. They're both exerting 5,000 newtons, so they're both equal, but they're going out on 15 degrees either side of north. So in this case, we're going to treat each one of these as a separate vector. So our first vector, which I've highlighted in blue, has a direction going of 345 degrees. So what I'm going to do is redraw that and place that as the first vector. And I've got that 15 degrees in there. And then what I'm going to do is add the next vector on, putting them nose to tail. So the next one I'm going to draw, which I'm going to highlight in yellow, I'm going to place its tail to the nose of the first vector, and that has a direction of 15 degrees. So what I can now see is by placing them nose to tail, I can see as one tugboat pulls at 15 degrees towards the east and the other pulls 15 degrees towards the west, that they will equal each other out, and I'll have my resulting vector. What we can do from here is perform some calculations and realise the angle between them is 150 degrees. We both know they're exerting 5,000 newtons each, and we can use some trigonometry. So we can use the cosine rule to calculate that the resultant vector will have a force of 9,660 newtons in a direction of 0 degrees. So now I'd like you to have a go at question 4. I'd like you to consider the two forces acting on the platform. And we can see that in between them there's actually an angle of 90 degrees as they both move away. One's got more of a force than the other. So I'd like you to place these nose to tail and draw in that resulting vector and use the cosine rule to calculate the magnitude of that resultant vector and also the direction because of the unevenness of the angles from north and the force, it will be slightly different to working in 0 degrees direction. So hopefully from your calculations, drawing those two vectors in, you'll notice as you place them nose to tail that the angle between them is actually 90 degrees, so we can use Pythagoras to find the resulting vector's magnitude, which is 5,831 newtons. And then using the tan ratio, we can find out that it's working on a bearing of 1 degree. So the resulting force acting on a body depends on a number of forces and their direction. When they talk about the angle between two forces, that's referred to when the forces are both directed towards or both directed away from a point. So here's two examples where I've got two forces directing away and the angle in between them is 30. In my next example, you can see that one force is going inwards and one is going outwards from this point here. So if we actually moved this vector over and placed it, we would find that the angle that's actually working between them is 146 degrees. In our last example, we have the canoeist. And this is a canoeist is trying to cross a 500-metre wide river. And normally he would paddle directly across from point A to point B at 6 kilometres per hour. So that's the result that he wants. He wants to get from point A directly across to point B. We can call that our resultant vector. However, the river is flowing parallel to the bank at 3 kilometres an hour. So going in this direction at 3 kilometres an hour. So obviously, if he swims straight across from point A, he is going to be taken downstream. So what we need to work out is what angle he's actually going to swim on so he does actually reach point B to take into account the flow of the river. So if we think about how we're going to draw this, from point A to point B, that's the result we want. So in order to counteract this 3 kilometres an hour that's happening on this side, we're going to have to get the canoeist to swim out towards the left of where he normally would, where he'd be travelling at 6 kilometres or swimming at 6 kilometres an hour. And here we have the riverbank. So we want to find what angle here, theta, to the bank is he going to swim on. So we've made a really nice right angled triangle here, and we can clearly see that we could use Pythagoras to solve it because we've got a 90-degree angle. So we could say the resultant is going to be the 6 squared minus the 3 squared, which would be 3 root 3 kilometres an hour, or 5.196 kilometres an hour as a decimal. We can then work out the sine of the angle. I'm going to find this angle in here, so I'm just going to call it alpha, which would be 3 over 6. So alpha would be the sine of a half. And knowing our exact values, we know that alpha would be 30 degrees. So our angle theta to the bank is going to be 60 degrees. So here we have our resultant speed, 5.196 kilometres per hour. And we want to find out how long it will take the canoeist to reach point B. So if we think about the fact that resultant speed of 5.196 kilometres should be the distance we want to travel, which is 500 metres, over the time, which we don't know. What I'm going to do is change this value, the 5.196 kilometres per hour, to metres, so 5,196 kilometres over 60 minutes over that hour. So when we solve this, we get x is 5.77 minutes. So it will take 5.77 minutes to get across from point A to point B. So all that work in previous years that we've done looking at hikers walking on a track from different checkpoints, looking at ships leaving a port, or even aeroplanes, what you were actually doing in all those diagrams was drawing vectors to represent their magnitude and their direction. And then by drawing them nose to tail, which is really important, one after the other, we can then find the resulting vector. Now I'd like you to have a go at the following set questions from Sadler Unit 1. Make sure you can recall and confidently use all your trig rules, and ensure that you draw your diagrams nice and clearly so you can see the resultant vectors.